What if you could send a message to your past self? Imagine warning yourself about a bad decision, or maybe sharing some winning lottery numbers. The idea of reaching back through time is a captivating thought. It has fascinated humans for centuries. Could we actually communicate with the past? The past holds a certain allure. It's filled with moments we cherish and experiences that shape us. It's no wonder we dream of revisiting those times. But is time travel just a fantasy, or could it be a real possibility? Today we'll explore the mind-bending world of time travel and the possibility of communicating across eras. Buckle up, because things are about to get really interesting. Let's dive in. Time travel has been a staple of science fiction for decades. From H.G. Wells' The Time Machine to the iconic DeLorean in Back to the Future, our imaginations have been ignited by stories of time-bending adventures. Movies and books often depict time travel as a thrilling yet perilous endeavor. These stories often serve as a launchpad for exploring the implications of altering the past or glimpsing into the future. But how much of this is pure fiction, and how much is rooted in scientific possibility? The truth is, the concept of time travel isn't confined to the realm of fiction. Scientists and physicists have grappled with the theoretical possibilities for years. While we haven't quite cracked the code to building a time machine, the laws of physics don't entirely rule it out. Before we dive into the potential science behind time travel, let's address the elephant in the room: the paradoxes. One of the most famous is the grandfather paradox. Imagine going back in time and accidentally preventing your grandparents from meeting. This creates a logical contradiction. If they never met, you wouldn't exist. And if you don't exist, how could you have gone back in time to change things in the first place? These paradoxes highlight the mind-boggling complexities of time travel. They force us to confront the very nature of cause and effect, and the potential consequences of tampering with the delicate fabric of time. But don't worry, the existence of these paradoxes doesn't necessarily mean time travel is impossible. They simply underscore the need for a deeper understanding of the laws of physics and the nature of time itself. So, are you ready to explore some of the fascinating theories that attempt to reconcile time travel with the laws of physics? Time travel challenges our fundamental understanding of the universe. We tend to think of time as linear, a straight line from past to future. But what if time is more like a fabric, a tapestry woven together with space? This concept, known as spacetime, is central to Einstein's theory of relativity. Imagine a trampoline as a representation of spacetime. A bowling ball placed in the center creates a dip, a curvature in the fabric. This curvature is what we experience as gravity. Now imagine an object with enough mass and energy to create a much deeper curvature, a tunnel or shortcut through spacetime. Could this be a portal to another point in time? It's a mind-boggling concept, but one that physicists have explored as a theoretical possibility. Shortcuts through spacetime are called wormholes. Picture them as tunnels connecting two distant points in the universe, or even two different points in time. While we haven't observed wormholes directly, their existence is consistent with Einstein's equations. However, there's a catch. Wormholes are thought to be incredibly unstable and microscopic. To make a wormhole traversable, we'd need something called exotic matter, a hypothetical substance with negative mass. Exotic matter, if it exists, could potentially prop open a wormhole long enough for something to travel through it. Right now, this is all highly theoretical, but the possibility, however remote, is enough to spark our curiosity. Einstein's theory of relativity also suggests that time is relative, not absolute. Time can be affected by factors like speed and gravity. The faster you travel, the slower time passes for you relative to someone who is stationary. This phenomenon, known as time dilation, has been experimentally verified. Atomic clocks flown at high speeds have shown slightly slower times compared to clocks on Earth. While the difference is minuscule at everyday speeds, it becomes more significant at speeds approaching the speed of light. Gravity also plays a role. Time slows down in stronger gravitational fields. This means that time runs slightly slower at sea level than on a mountaintop, where gravity is slightly weaker. These effects, while fascinating, are not yet a means of traveling to the distant past or future. However, they demonstrate that time is not the rigid, unchanging entity we often perceive it to be. It's a fluid concept, subject to the laws of physics. Let's talk about black holes. These cosmic giants are regions of spacetime where gravity is so intense that nothing, not even light, can escape. They form when massive stars collapse. But what do black holes have to do with time travel? Einstein's theory says black holes warp spacetime, creating a singularity. At the singularity, time stands still. Imagine approaching a black hole. Time would slow down for you, you'd see the future unfold. But crossing the event horizon is a one-way trip. Once you're in, there's no coming back. Black holes offer a glimpse into time, but they're not practical time machines. Another intriguing concept in the realm of time travel is the idea of closed time-like curves, or CTCs. Imagine a path through space-time that loops back on itself, creating a closed loop. If you were to travel along this loop, you would essentially be traveling through time. CTCs are predicted by Einstein's equations under certain extreme conditions, such as the presence of rotating black holes or wormholes. However, the existence of CTCs raises some serious paradoxes, such as the possibility of changing the past or encountering your past self. One proposed resolution to these paradoxes is the Novikov self-consistency principle. It suggests that if you were to travel back in time, you would be bound by the laws of physics to act in a way that is consistent with the past that has already occurred. In other words, you wouldn't be able to change the past, even if you tried. Whether CTCs actually exist, and whether the Novikov principle holds true are still open questions. But they highlight the mind-bending possibilities and challenges that arise when we try to reconcile time travel with our current understanding of the universe. Let's venture into the realm of hypothetical particles. Have you heard of tachyons? These are theoretical particles that always travel faster than light. According to Einstein's theory of relativity, nothing can travel faster than light in a vacuum. However, tachyons are thought to have imaginary mass, which means their energy decreases as their speed increases. This bizarre property has led some physicists to speculate that tachyons could be used to send messages back in time. Imagine sending a tachyon signal to the past. Because it travels faster than light, it would arrive before it was sent, at least from the perspective of an observer in a different reference frame. However, there are major challenges with this idea. First, we've never actually detected tachyons, and their existence remains purely hypothetical. Second, even if tachyons do exist, it's unclear how we would harness them to send meaningful messages. The concept of tachyonic communication is highly speculative, but it's a fascinating example of how exploring the fringes of physics can lead to mind-bending possibilities. Now let's delve into the strange world of quantum mechanics, where things get really weird. One of the most mind-boggling phenomena in quantum mechanics is entanglement. It occurs when two particles become linked, even when separated by vast distances. When you measure the state of one entangled particle, you instantly know the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, seems to violate the principle of locality, which states that an object can only be influenced by its immediate surroundings. So, how does this relate to time travel? Some physicists have proposed that entanglement could be used to send messages instantaneously, potentially even across time. Imagine entangling two particles and sending one of them into the past. Could we then manipulate the remaining particle in the present to send information to the past? The idea is highly speculative, and there are significant theoretical challenges to overcome. However, quantum entanglement remains one of the most intriguing areas of research in physics, with the potential to upend our understanding of time and space. We've explored some mind-bending theories about time travel, but why does time seem to flow in only one direction? This perceived directionality of time is often referred to as the arrow of time. Some physicists believe it's linked to entropy, a measure of disorder. The second law of thermodynamics states that entropy always increases. Things tend to become more disordered over time. The arrow of time remains a topic of debate and ongoing research. Let's dive back into the quantum realm for a moment and explore an experiment that has profound implications for our understanding of time. It's called the quantum eraser experiment, and it challenges our notions of cause and effect. In this experiment, a pair of entangled photons is created. One photon is sent through a double-slit apparatus, creating an interference pattern on a screen. The other photon is sent along a different path. Now here's where things get really weird. If we measure which slit the first photon went through, the interference pattern disappears. It's as if the act of observation collapses the photon's wave function and forces it to choose a definite path. However, if we erase the information about which path the first photon took by manipulating the second entangled photon, the interference pattern reappears. It's as if we've somehow rewritten the past by erasing the information about which path the photon took. The quantum eraser experiment is a mind-boggling demonstration of the non-local nature of quantum mechanics and the interconnectedness of entangled particles. It suggests that actions in the present can influence events that have already occurred, at least at the quantum level. Imagine a future where time travel is a reality. Tourist agencies offer trips to ancient Rome, the Wild West, or even prehistoric times. But what would the implications of such time tourism be? For starters, the sheer number of time travelers could have a significant impact on the past. Imagine thousands of tourists flocking to witness the signing of the Declaration of Independence or the eruption of Mount Vesuvius. The presence of these observers, however well-intentioned, could disrupt the very events they came to see. There's also the issue of paradoxes. What happens if a time traveler accidentally steps on a butterfly in the Jurassic period? Could such a seemingly insignificant act have unforeseen and catastrophic consequences in the future? The potential for paradoxes and unintended consequences raises serious ethical concerns about the wisdom of time travel. It suggests that even if time travel were possible, it might be a technology best left unexplored or at least approached with extreme caution. So where do we stand on the question of time travel? Is it a scientific possibility, a philosophical conundrum, or simply a product of our imaginations? The answer, as with many things in science, is that we don't know for sure. We've explored some fascinating theories, from wormholes to quantum entanglement, that suggest time travel might not be entirely impossible. However, these theories remain highly speculative, and there are significant theoretical and practical challenges to overcome. The laws of physics, as we currently understand them, don't explicitly prohibit time travel, but they do impose constraints that make it extremely difficult to achieve, at least with our current level of technology. Whether time travel will one day transition from the realm of science fiction to scientific reality remains to be seen, but the pursuit of this elusive dream continues to inspire our curiosity, challenge our assumptions about the universe, and push the boundaries of human ingenuity. Time travel remains one of the most intriguing and perplexing mysteries of the universe. It's a concept that has captured our imaginations for centuries, inspiring countless stories, theories, and scientific inquiries. While we haven't yet cracked the code to building a time machine, the possibility, however remote, continues to beckon us. The laws of physics, as we currently understand them, offer both glimpses of hope and formidable challenges. Wormholes, time dilation, quantum entanglement, these are not mere plot devices from science fiction but concepts rooted in theoretical physics, pushing the boundaries of what we thought possible. Yet, the paradoxes of time travel, the arrow of time's seemingly unyielding direction, and the sheer complexity of the universe remind us that our journey of understanding is far from over. The quest to unravel the mysteries of time is a testament to our insatiable curiosity as a species. It's a journey driven by a deep-seated desire to comprehend our place in the cosmos and to explore the vast unknown that lies beyond the limits of our current understanding. So what do you think? Is time travel an unrealistic dream, or could it one day be our reality? Share your thoughts, theories, and wild ideas in the comments below. The beauty of science lies in its ability to spark our imaginations, challenge our assumptions, and inspire us to keep asking questions. Thank you for watching Time Pilgrimage, and as always, please remember to subscribe and like. If there is a topic that you would like to explore, please drop a comment. Until next time, keep exploring, keep questioning, and keep looking up at the stars. The universe is full of wonders waiting to be discovered, and who knows, maybe time travel is one of them.